Hey guys, so in this video we're gonna go through 4 essential exercises when dealing with implicit differentiation, and of course I'm not saying that only these 4 exercises are enough for you to score a 7 in your assessment, in your exam. However, these are essential exercises that you need to know how to deal with. We have the regular standard find dy dx, which is the derivative of y with respect to x implicitly. That's type number 1, or we can call it exercise number 1. We also have finding tangent lines to these curves. These are implicit curves, and we're going to find through an example a tangent to this curve at a given point. That's exercise number 2. Type number 3, or exercise number 3, finding horizontal or vertical tangents. These are 2 different types, by the way, 2 different cases. For horizontal we do something, for vertical we do something else. And type number 4, which is to find the second order derivative, or the second derivative of y with respect to x. Now you can also label this d2y dx squared. That's how we reference the second order derivative. And these are 4 essential, crucial exercises that you need to know how to deal with. Let's start with type number 1, the simplest case, which is to find dy dx. Now we have find dy dx given that x squared times cosine of y plus sine of 2y is equal to x times y. It is very important to restate that y is a function of x, which means that if you're differentiating terms like x squared or 3x, you get 2x and 3 respectively. However, if you're differentiating terms which involve y, that means that you need to use the chain rule. So for example, the derivative of y cubed is 3y squared times dy dx, or times y prime. So keep that in mind. Let me actually place these examples right here. While the derivative of x squared is equal to 2x, the derivative of y squared, given that y is a function of x, and right now we're talking about the derivative with respect to x, is 2y times y prime, or 2y times dy dx. It's shorter to write y prime, but if you want to write it as dy dx, that's fine as well, of course. Now over here we have a product, and we also see a product right here, so that means that we're going to use the product rule for these 2 terms, and we will use a chain rule, or actually an additional chain rule over here, given that we have the sign of not just y but 2y. So we're going to use the chain rule, and then another chain rule will show up inside this first chain rule. But let's see that when it emerges, let's cross that bridge when we get to it. Now, starting with the product rule, we have the derivative of x squared, which is again 2x times cosine of y. So we differentiate the first portion times the second one, plus the first one times the derivative of the second one. So the derivative of cos is negative sine of whatever's inside. In this case, what's inside is the arc y, times the derivative of y, given that y is a function of x. So right now we're applying the chain rule. So right now you can write dy dx or y prime, plus the derivative of sine of 2y, which is cosine of 2y, times the derivative of 2y, which is 2, times the derivative of y, and this is the second chain rule, which is dy dx or y prime. All of this is equal to 1 times y, and again we're using the product rule, plus x dy dx. Now a good idea in this step is to move everything that has y prime in it to the left hand side, and everything that does not to the right hand side, which means that we're going to have negative x squared sine of y times y prime, plus 2 cosine of 2y times y prime, minus x y prime, equal to this y here, minus 2x cosine of y. By doing so, we can factor out all the y primes, which will allow us to rewrite this expression as negative x squared sine of y plus 2 cosine of 2y minus x equal to y minus 2x cosine of y. So y prime, which is dy dx, it is equal to y minus 2x cosine of y over all this. And this is our final answer. And there you go. Now for exercise number 2, we're going to take the advantage of the fact that we actually have differentiated this already and use the same equation to find a tangent to this curve right here at a given point. Now I'm going to select a point, and it needs to be a point that the equation actually, the graph of this equation actually crosses. And the point that we're going to use is the point 0 comma pi over 2. So let's build this exercise. Find the tangent to the curve, and we're going to use the same one, x squared cosine of y plus sine of 2y equals x times y at the point P, which is the point 0 pi over 2. Now, how can you check if this point, you don't need to worry about this because obviously in the IB exam, they will give you a point that the curve actually crosses. But if you want to test it out, you can replace x by 0, which is exactly this coordinate right here, and y by pi over 2. So we have pi over 2 right here, 0, 0, pi over 2. Now on the right hand side we get 0, which means that if this curve actually crosses this point, we should get 0 on the left hand side as well. On the left hand side we have 0 times something plus sine of 2 pi over 2, which is sine of pi, which is equal to 0. So this point actually belongs to the curve. The curve crosses this point. Now the good news when addressing exercises that involve tangent lines is the fact that you don't need to carry out the differentiation process all the way to the last step. So for example, in the previous example, which involved the same equation, we went through all of these steps in order to get dy dx, which ultimately will give us the slope of the tangent line. Now, why do we not need to do that? Well, because on the first step, which is the first step of this differentiation process, which is, and let me remove all the rest, this one right here, we can already replace, and let me make this white, the coordinates of the point. So x being equal to 0 and y being equal to pi over 2. Why can we do that? Well, the only things that we need in order to find the equation of this tangent is the slope, which we're going to get right here through evaluating this y prime, and a point. We have the point 0 comma pi over 2. We only need y prime when replacing 0 and pi over 2 into this equation. So let's do that right now. Given that we're multiplying this by 0, we have 0 over here. We have 0 over here. You see how much you can save, how much time you can save by replacing this point in this step right here. This guy is 0 as well. We have cosine of 2 times pi over 2, which is cosine of pi, which is -1. Over here, we just have 2 times y prime, so 2y prime. And right here, we have 1 times y, so pi over 2. So all there's left is -2y prime equal to pi over 2. That means that y prime, which by the way is the slope of the tangent line, is equal to -pi over 4. Now that we have the slope, we just need to replace it with the point in the point slope form of the equation of the line. So all that we have left to do is replace this by -pi over 4. This guy is 0, and this one, it is pi over 2. Therefore, we have y minus pi over 2 equals -pi over 4 times x, which means that y is -pi x over 4 plus pi over 2. And this is the equation of the tangent at 0 pi over 2. And by the way, this is what the graph of the curve looks like. And we can see in this blue line right here, which by the way crosses the point 0 pi over 2, the tangent at that point. Now let's move to exercises 3 and 4. Alright, so for exercise number 3, we're going to find all horizontal and vertical tangents to the graph of x squared plus y cubed minus 3y equals 4. Now, in this case, we do need to carry out the differentiation process all the way to the end. We need to find what dy dx is, so let's do that first. In this case, it's a simpler derivative. So we have the derivative of x squared, which is 2x, plus the derivative of y cubed, which is 3y squared, times, given that we need to apply the chain rule, dy dx minus 3 times, and careful with this one, the derivative of negative 3y is not negative 3, it's negative 3y prime, equal to, and careful here as well, by the way, it's equal to 0. Now we should move every term that does not include y prime to the right, factor out a y prime, and right here we can and should divide both sides by 3y squared minus 3, which gives us negative 2x over 3y squared minus 3. Now let's start with the vertical tangents, because these are the less common ones. You're going to have a vertical tangent line when the derivative is undefined, which means that y prime or dy dx is undefined. How can we make this undefined? Well, that will be by dividing by 0. For example, in this case, we have a fraction, we have a ratio, which means that this is going to cease to exist or to be true or to be valid when 3y squared minus 3 is equal to 0. So let's break this down into a few cases. Vertical tangents first. So the curve will have vertical tangents when the denominator is equal to 0, which is undefined. So when 3y squared minus 3 equals 0, which means that 3y squared is equal to 3, which means also that y is either positive or negative 1. Now, these are, of course, not the equations of the vertical tangents, because vertical tangents have the following equation: x equals something, right? It's an x value. So what do we do with these y values? We place them back into the equation. So we have, for y equals 1, x squared plus 1 cubed minus 3 times 1. This equals 4, which means that x squared minus 2 equals 4, which means that x squared equals 6. And we have a couple of vertical tangents from this condition only, which are positive and negative root of 6. Now, what about for y equal to negative 1? We do the same thing. We replace negative 1 into the original equation, which means that we get x squared plus negative 1 cubed minus 3 times negative 1 equal to 4. X squared minus 1 plus 3 equals 4. The two equations that we have are positive and negative root of 2. So we got in total 4 vertical tangents. Now, what about the horizontal tangents or tangent? Because in this case, we're only going to get one. Well, we find horizontal tangents when dy dx is equal to 0, meaning the instantaneous rate of change equals 0. The slope is 0. So we're going to take y prime and equal it to 0. So the curve will have horizontal tangents when y prime, which is dy dx, which in this case is negative 2x over 3y squared minus 3 equals 0, which means that the numerator is equal to 0. You can cross multiply, for example, this by 0, and this term would disappear, or just take into account that the numerator being equal to 0 is what's going to make the whole fraction be equal to 0. So if negative 2x is equal to 0, that means that x equals 0. And we use a similar strategy right here. We substitute x equals 0 back into the original equation. So we have 0 squared plus y cubed minus 3y equal to 4. Y cubed minus 3y equals 4. Now this is not an equation that we can solve using any sort of algebraic method, so we need to rely on the calculator for this, for finding this solution. And we get y equals 2.1958 ... which is 2.20 rounding to 3 significant figures. So what is the equation of the tangent? Y equals 2.20. Now we can see these tangents if we draw the equation, the curve that is represented by this equation, and these tangents. And this is what we get. This is the curve in gray. We have the vertical tangents and the horizontal one right here in blue. The vertical in red, the horizontal in blue. All right, so on to the last exercise, exercise number 4. Now, what we have here is we need to find the second order derivative of y with respect to x, given that 3xy minus y squared is equal to 10. This is the equation that we have. Now, we know that y is a function of x, and to find the second order or the second derivative, we need to go through the process of finding the first one first. We're going to use it when calculating the second one, of course, and in more than one way. Now let's go through the hoops. So we have a product right here, which means that we need to use the product rule. 10 is a constant, so careful with this. The derivative of 10 is just 0. And we have the derivative of y squared over here, which is 2y dy dx. So we have 3 times 1 times y plus x y prime, the product rule being applied, minus 2y y prime equal to 0. We can FOIL here, 3y plus 3x y prime minus 2y y prime equal to 0. We can move also the 3y to the right and isolate or factor out the y prime on the left, which gives us the following. Y prime times 3x minus 2y equals negative 3y. Therefore, our y prime, which is dy dx, equals negative 3y over 3x minus 2y. Now, this is the first derivative, which means that y prime prime, or d2y dx2, is the derivative of this with respect to x. So right now we have a quotient rule where negative 3y is the term in the numerator and 3x minus 2y is the term in the denominator. So keeping that in mind, we have the derivative of the function on top, or the term on top, which is negative 3, careful here, y prime, times the bottom one, the denominator one, minus the top one times the derivative of the one in the denominator, which is 3 minus 2 y prime over the denominator squared. Now let's just FOIL these first before, and if you're guessing, the next step, which is to replace all the y primes by dy dx, the dy dx that we found in the previous part. But let's FOIL it first. So we have negative 9x y prime plus 6y y prime plus 9y minus 6y y prime over 3x minus 2y squared. We can cancel out these y primes, which simplifies a lot, and we are going to replace this y prime by negative 3y over 3x minus 2y, which gives us negative 9x times that plus 9y over 3x minus 2y squared, which we're not going to expand. The denominator will just stay there. Now you can simplify this quite a bit if you put 3x minus 2y as the common denominator in the numerator, which means, so placing 3x minus 2y as the denominator of the numerator, we have negative 9x times negative 3y plus 9y times this new denominator, which is 3x minus 2y, all of this over 3x minus, this is a minus, 2y squared. For this numerator, we get 54xy minus 18y squared, and given that we have a quotient between fractions, the final answer will be 54xy minus 18y squared over 3x minus 2y, not squared, but cubed. So as you can see, finding the second order derivative does take a while, given that you have to use the first derivative in order to get there. So that is it, the 4 types of implicit differentiation exercises that you need to know.